Hello everyone. Today again we are going to discuss the last part of this chapter, that is wave optics, in this session 10. So that is the polarization of light. So polarization means, the definition first we will study: the phenomena by which the vibrations of the waves in a beam are restricted to the particular plane, that is called as polarization. Generally, if you considered an ordinary light, the vibrations will be taken place in all the directions, that is perpendicular, parallel. So all the directions the vibrations are taking place in case of the ordinary light. But polarization means you have to restrict that vibration in particular plane. That phenomena itself is called as it is a polarization. Means in ordinary light both the vibrations you are getting perpendicular as well as the parallel, but whenever we are getting the polarized or the phenomena, if you are doing the polarization phenomena, then what happens, we are going to restrict the vibration in particular plane. Means either you can consider the perpendicular vibrations or you can consider the parallel vibrations. So such type, one particular restriction or one particular direction, if the vibration is taking place, that phenomena itself is, we can call it as it is a polarization. So next, if a beam of light it is produced in which the vibrations are confined to only one plane, that is called as plane polarized light. So afterwards the polarization process that taken place, then all these vibrations which are restricted or which are confined to only one plane. So which one you decide, it is parallel or perpendicular, whatever the vibration if you are desired, then that we can get, that is vibrations which are confined or which are restricted to only one plane. Such type of light is called as it is a plane polarized light. So in the diagram, just you observe the first diagram, that source x, y, z, whatever we have taken, it is an ordinary light, or generally we call it as it is unpolarized light. So unpolarized light means the vibrations which are taken place in all the directions. So x-axis is also there, y-axis is also there, and z-axis. So there is no particular direction for the vibration in this case. That is an ordinary light or unpolarized light. So coming to the second diagram here, that unpolarized light, same thing we have taken, but in first diagram it is the top view of that unpolarized light, and in second diagram whatever the unpolarized light it is written, that is the front view. So the front view we have taken. So the vertical lines which are represented by the parallel vibrations, and the dot which are taken, that black dots, that is represented the perpendicular vibrations. So whenever an unpolarized light which is passes through the certain crystal, then you are getting it as polarized light. Polarized means the vibration which is restricted to only one plane. So here the perpendicular vibrations are absorbed, only the plane vibration or parallel vibrations which are come out here. So the diagram you can see now in figure A, that is vibrations in the plane of paper, means parallel to the plane of paper. Dotted line means it is vibrations which are perpendicular to the plane of paper. So unpolarized light, which consists of both the vibrations, parallel as well as perpendicular. So whenever the polarization process is taken place, at that time the polarized light or the plane polarized light, so that is, it is restricted to only one plane. So in this case the perpendicular vibrations is not occurred in the second diagram, that is in main thing, the main diagram, just to observe the perpendicular, the dotted lines which is not absorbed or observed, but only the plane, that is parallel vibrations which are observed. Means the unpolarized light or the ordinary light which is restricted in moving in only one plane, or the vibrations which are restricted in only one plane. So such process is called as the polarization. Next we will discuss the plane in which the vibration of polarized light is taken place is called as plane of vibration. So in what plane it is, either it is in perpendicular plane or the parallel plane, in what plane the vibration of the polarized light that will be taken place, it is called as it is a plane of vibration. And the next is the plane in which the vibration of polarized light is restricted, it is called as plane of vibration. So in the plane in which the vibration of polarized means in which direction you are going to restrict, whether it is parallel or perpendicular. That restricted direction itself is called as it is a plane of polarization. So next we will discuss regarding the polarization that can be produced with the help of certain following methods. How you can produce means, one is by reflection, another one is by refraction, and another one is the double refraction and scattering, as well as the selective absorption, or we call it as dichroism. So with these all methods we can get the polarization. So polarized light, if you are to get the certain methods we are using, one is refraction, reflection and double refraction, scattering and selective absorption or dichroism. So in this, first we will discuss regarding the polarization by reflection method. So in 1808, Malus is a name of scientist who discovered the simple way of producing plain polarized light by reflection. So with the help of a reflection we are getting the polarized light. So it was found that when a beam of ordinary light is refracted by the surface of transparent medium like a glass or a water, the reflected light is partially polarized. So when an ordinary light or unpolarized light, if it is incident on the transparent material like a water or a glass material if you take, then the light will be reflected. So that reflected light is partially polarized. Partially means some of the vibrations which are absorbed and some of the vibrations which are present here. So it is not completely polarized, you can say. So the degree of polarization which will be depend upon the angle of incidence. As the angle of incidence gradually increases, the degree of polarization is also increases, but at a particular angle of incidence, the reflected light is completely plane polarized, means completely it is restricted in only one direction at a particular angle of incidence, and that angle of incidence is called as Brewster's angle or polarizing angle. So you have to remember this. Brewster's angle or polarizing angle means it is one particular angle of incidence, the reflected light is completely plane polarized. And if the angle of incidence, if you are going to further, if you are increasing further after this Brewster's angle, then the degree of polarization, of course it is going to decrease, it is not going to increase after the Brewster's angle, it is going to decrease. So next we will study regarding what is Brewster's law. So for that, once again we have taken the statement here. The Brewster's angle for the surface, it is an angle of incidence for which the reflected light is completely plane polarized, or generally it is polarized. But coming towards the next one, it is the Brewster's law. So Brewster's law states that it is the tangent of a Brewster's angle which is equal to the refractive index of the material of the reflector. So this is known as the Brewster's law. The tangent of the Brewster's angle means it is a tan of Brewster's angle. Brewster's angle means the angle of incident. At particular angle, what happens? The reflected light is completely plane polarized. So tan of this Brewster's angle, which is equal to the refractive index of the material, because the angle, whatever the light which is incident on certain transparent material like a glass or a water. So these are materials having certain refractive index. So that is equal to the refractive index of the material of that reflector. So it will be given by n is equal to tan IB, where n is the refractive index of the material and tan IB is nothing but it is the tangent of the Brewster. The tan is nothing but the tangent angle. So tan of the Brewster's angle. Brewster's angle means it is an angle of incident at a particular point. You are getting it as at a particular angle the reflected light is completely polarized. Therefore angle of incidence, instead of I we have taken it as IB. Next, when the angle of incidence on the surface is equal to the Brewster's angle, suppose whenever the angle of incidence on the surface, if it is equal to the Brewster's angle, then it has to obey one condition, that is the reflected and the refracted rays are perpendicular to each other. So if it is the angle of incidence equal to the Brewster's angle, then one reflected ray and another one refracted ray, both are perpendicular to each other. Whether this rule it will follow or not, we are going to check now with the help of the derivation of the Brewster's law. So for that we have considered one diagram. Just in diagram also you can observe that AO, that is an unpolarized light, both parallel and perpendicular vibrations are there, and certain part it will be reflected along with OB. Here the perpendicular vibrations are there, not the parallel vibration, and some part it will be refracted through the OC. So we have to consider a beam of unpolarized light incident at an angle which is equal to the Brewster's angle, that is IB. In some book they have given it as IP also. IP means polarizing angle on the surface of the transparent material XY. So XY is one transparent material, AO is the incident ray which is going to incident with an angle, that is an Brewster's angle, that is IB, and XY, that transparent material which is having certain refractive index, that generally we call N. Therefore our AO is a incident ray, the ray which is reflected along OB and refracted along OC. So after the incident, certain part of ray it will be reflected along OB and some part it will be refracted along OC. Let R be the angle of refraction. Next, from the figure, angle AOM, that is equal to IB, that is an angle of incidence with the help of a Brewster's angle, that is IB, and similarly angle NOC is equal to R, that is a refracted angle, that is angle of refraction. Since angle of reflection is equal to the angle of incidence, here the angle of incidence is how much? The same amount of angle of reflection we are getting, that is angle MOB is equal to also IB term. Next, the continue part, the same diagram again we have taken, but from the Brewster's law. What is our Brewster's law? It is N is equal to tan IB, means the tangent of a Brewster's angle is equal to the refractive index of the material. N is the refractive index, tangent of an angle means it is tan of IB. But tan IB we can write it as it is sin IB by cos IB. Next, from Snell's law of refraction, what is Snell's law of refraction? It is the refractive index N is equal to, it is sin I by sin R. So sin I is replaced by sin IB because here incident angle is IB, and similarly sin R it is as it is. So both are the equations which are starting with N, that refractive index. So we can compare both the equations. Therefore whenever we are going to compare that N is equal to, that is sin IB by cos IB, we are getting it equal to sin IB by sin R. So sin IB term is same, only the different term is cos IB is equal to, now what happens, it is sin R. So now we are going to replace this with a cos term. Therefore sin R if you are getting means it is cos of 90 minus R. Of course cos of 90 minus R means it is changed, therefore we are getting it as sin R. Therefore we can write now IB is equal to, because cos IB is equal to, we got it as it is cos of 90 minus R. Therefore IB is equal to, it is 90 minus R, or IB plus R is equal to, we write it as it is 90 degree. Therefore from the figure, angle MON, which is a straight line, that angle is equal to 180 degree. Therefore angle MOB plus angle BOC plus angle NOC, all these must be equal to 180 degree. Then what is our angle MOB? Angle MOB is again the angle of incidence which is same as the angle of reflection, that is IB itself. Angle BOC which is not known for us, so write it as it is, plus angle NOC, it is an angle of refraction, that is R, that equal to 180 degree. But already in previous just we have got the value for IB plus R. So substitute the value, angle BOC as it is plus IB plus R is equal to 90 degree we have calculated. So substitute that 90 degree is equal to 180 degree, or angle BOC is equal to 180 minus 90, therefore we are getting it as 90 degree itself. So this angle BOC is nothing but what? It is the angle between the reflected ray and the refracted ray. So already I told, whenever the angle of incidence is equal to the Brewster's angle, it has to obey one condition, that is whenever it is a Brewster's angle, the reflected ray and the refracted ray both are perpendicular to each other. So that is angle BOC. It is one reflected ray. BO is the reflected ray. OC is the refracted ray. Therefore, the angle between them is the 90 degree. Here we got according to the Brewster's law. So thus, the reflected and the refracted rays are perpendicular to each other when light is incident at the Brewster's angle. So this is regarding the Brewster's angle. Next we will discuss regarding the double refraction or birefringence. Already we know in case of the polarization, how we are going to produce the polarization with the following methods. That is, one is by reflection and another one is by refraction. Now it is a double refraction, or generally we call birefringence. So what is a double refraction means? When a beam of unpolarized light from a source is allowed to pass through certain crystal. So that is, an ordinary light, if it is passed through certain crystals, the crystals like a calcite crystal or a quartz or a mica, then you are getting, of course we have to get one refracted ray. But in this case what happened? The two refracted rays are come out from the crystal. So this phenomena is called as double refraction. So the two refracted rays, generally we call them, one ray it is called as ordinary ray, we can call it as it is O ray, and another one is called as extraordinary ray, it is E ray. So in the diagram just you observe, it is first one is the unpolarized light or the ordinary light. Whenever if we are passing through the crystal, then that time what happens? Two refracted rays we are getting. One is ordinary ray and another one is extraordinary ray. So there are certain definitions are there in this. And what is ordinary ray and what is extraordinary ray? What all the laws it will be obeys, that we are going to discuss now. The refracted ray which obeys the laws of refraction. Suppose if it is obeying the Snell's law, that is ordinary ray, it will obey the Snell's law, but the extraordinary ray which is not going to obey the Snell's law. And similarly, ordinary ray, that is when a beam of light is incident perpendicular to the surface, this ray passes without deviation. The ordinary ray, without deviation it will pass out, but the extraordinary ray it will deviate despite it is normal incident. And similarly, ordinary ray have equal velocity in all the direction. Therefore we have written that VO and VE in the diagram. VO is the velocity for ordinary ray, VE is the velocity for the extraordinary ray. So ordinary ray have equal velocity in all the direction, and extraordinary ray have different velocities along different direction. So these are the certain points you have to remember regarding the double refraction, that is both the rays are emerged out from the crystal. So what are the rays property, just you can remember. So next, suppose if you are considered a positive crystal like a quartz, the velocity of ordinary ray is more than that of the extraordinary ray. So VO is greater than VE. Hence the refractive index of the crystal for ordinary ray is less than that of the extraordinary ray. In this case what happens? The refractive index of ordinary ray is less than the refractive index of extraordinary ray. Similarly, if you are considered a negative crystal like a calcite crystal, the velocity of ordinary ray is less than that of the extraordinary ray, VO is less than VE, and hence the refractive index of the crystal for the ordinary ray is more than that of the extraordinary ray. Therefore NO is greater than NE. But for a double refracting crystal, there will be one or more directions along which the velocities of ordinary ray and extraordinary ray are equal. But whenever if you are consider it is a double refracting crystal, the ordinary ray and the extraordinary ray velocities are equal, and the direction along which the velocities of ordinary and extraordinary rays are equal, that is called as the optic axis of the crystal, and there is no double refraction along the optic axis. Similarly, the crystals such as a quartz, calcite and tourmaline have one optic axis, and that is called as uniaxial crystal. If the crystals such as selenite, mica and borax, they have a two optic axis and they are called as biaxial crystals. And similarly, one more, the method we know, it is a dichroism. Dichroism means Certain doubly reflecting crystals also exhibit the property of absorbing unequally the ordinary and extraordinary rays. So they will absorb certain rays unequally, that ordinary and extraordinary rays. Certain property of the crystal is called as selective absorption, or generally we call dichroism. So next we will discuss regarding the polarides. Just to observe the diagram. Polaride means it is a device which is used to produce a plane polarized light. So polaride, which is consist of a long chain of molecules which are aligned in a particular direction. So when an unpolarized light which is falls on the polaride, at that time the electric field vector or a light vector which are oscillating in the direction of alignment of the molecule of the polaride, that will be absorbed. However, the electric field vector oscillating in the direction perpendicular to the alignment of the molecules, they will pass through the polaride. Thus, the transmitted light has an electric field vector oscillating perpendicular to the direction of alignment of the molecules of the polaride. Thus, the transmitted light is known as linearly or plane polarized light. So, in diagram just to observe, that is first one is an unpolarized light. If it is passes through the polaride, we are getting the perpendicular lines are absorbed, only the parallel lines are pass out. So, in figure A and figure B also just to observe. Next we will study regarding this. So, the same diagram if you have taken. When two polarides are parallel to each other, that is their polarizing directions are parallel to each other, then the polarized light is transmitted by the first polaride is also transmitted by the second polaride, is shown in figure A. So, in figure A just to observe the two polarides, if you are taken, both the polarized directions are parallel to each other, then whatever the polarized light which will be transmitted with the first polaride, that same will be transmitted to the second one without any loss. Thus, next the second diagram if you consider, when the two polarides are crossed each other, that is their polarizing directions are mutually perpendicular to each other. So, in the figure B just to observe, one polaride is parallel and another polaride is perpendicular. Then the light which is transmitted by the first polaride is completely blocked by the second polaride as shown in the figure. So, here whatever the light which is passed through the first polaride, which is not going to pass through the second polaride, because it is opposite to that, because all the vibrations which are stopped here. Therefore, no light is observed in the second case. Next, this will be done with the help of the experimental verification of the polarization of light, that is a transverse nature of light. So, for that again we have considered the diagram here. So, here two polarides we have considered, that is one is polarizer P and analyzer A. Let both polarides are placed in such a way that their path axis or the polarizing directions are parallel to each other, that is in figure A just to observe. So, in this case polarizer as well as analyzer both are having the parallel direction. So, whenever ordinary light which is passes through the polarizer, the same amount of some amount of, that is perpendicular vibrations are observed and that will be passed through, and whenever that polarized light that will also pass through an analyzer, the same amount or some amount is reduced, that will only we are giving now. When an unpolarized light or ordinary light which is incident on the polaride P, it is found that the intensity of light is transmitted by the polaride A, it is reduced to half of the original value of the intensity of incident light. Similarly, consider the second diagram. Now place the polaride P in such a way that their path axes are perpendicular to each other. Here polarizer P is parallel and analyzer is perpendicular to it. So, when ordinary light which is incident on the polaride P, it is found that the intensity of light it will transmitted by the polaride A is 0 here, because the perpendicular vibrations are also absorbed and therefore we are not getting any light. This experiment further shows that the light is transverse in nature. So, below figure shows that the polaride are in three different positions. So, just to observe the three diagrams here. Here also we have taken the two polarides, one is one red colors and another one black color we have taken. So in figure A or in position A, the polarides are at 0 degree, means both are parallel to each other. So both are parallel means we are getting, it is allowing the maximum light. So in whatever the light which is transmitted through first one, the same it will transmit it to the second one without any loss. Therefore it is allowing the maximum light. Suppose in position second or the figure 2, the Polaroid 2 which is rotated to certain angle, then the shaded portion will show the retarded light. Suppose if it is tilted with certain angle, at that time the portion whatever it is overlapped with each other, that much amount of light it will be cut out. So the half of the radiation or half of the polarized light it will come back. And the third one, in this position C, it shows that the rotation is 90 degree or 90 degree rotation of Polaroid 2, which will helps what? The blocking the light in the overlapping position. So whenever both the lights, both the polarides, if you keep that is perpendicular to each other, at that time there will be no light, that is intensity becomes 0, you can see. So this is the three conditions you have to know. So next we can discuss regarding what is Malus law. Malus law means, this law states that the intensity of the polarized light transmitted through the analyzer varies as the square of the cosine of the angle between the plane of transmission of analyzer and the plane of the polarizer. So whatever the intensity of polarized light is there, which is proportional to the square of the cosine of the angle between the plane of the transmission of analyzer as well as the polarizer. So for that we have considered one diagram. So according to the diagram, E be the amplitude of the light which will be transmitted by the polarizer, and theta is the angle between the planes of polarizer and the analyzer. In that we have to resolve this E into the two components. First one is E cos theta along OP, that is parallel to the plane of transmission of analyzer, and E sin theta along OV, which is perpendicular to the plane of transmission of the analyzer. Already we know, if it is a perpendicular, we are not getting any light, the amplitude becomes a 0. So only one will be left out, that is only E cos theta along OP. The component is transmitted through the analyzer. Therefore already we know intensity is directly proportional to the square of the amplitude according to the Malus theorem. So intensity of transmitted light through the analyzer, that will be given by, what is our intensity is intensity I, which is directly proportional to the amplitude square, that is E cos theta the whole square, or we can write it as it is I is equal to K into E square cos square theta, where K E square is equal to, we can write it as I naught, that is intensity of the incident polarized light. Therefore our equation becomes I is equal to I naught cos square theta, or I is proportional to cos square theta, which is known as the Malus law. So Malus law special cases are there that we are going to discuss now. In that, first one, when theta is equal to 0 degree, that is planes of polarizer and the analyzer or their polarizing directions which are parallel to each other. So whenever both are parallel to each other, then our cos theta is equal to cos 0. So cos 0 is 1, therefore our I is equal to I naught we are getting. Thus the intensity of incident plane polarized light does not change whenever both are parallel to each other. And the second case, when theta is equal to 90 degree or pi by 2, then the planes of polarizer and the analyzer are perpendicular to each other, then our cos theta becomes a cos 90 or cos pi by 2, that is equal to 0. Therefore I becomes 0, the intensity is 0. So whenever both the polarides are arranged in perpendicular to each other, then there will be no intensity. Hence the intensity of incident plane polarized light becomes 0. And the last one we are going to discuss regarding what are the uses or the applications of the polarides. First one is, polarides are used to produce the plane polarized light. Already we know, that is polarides are used to produce the or detect the plane polarized light. So for that, when a beam of a light from a source which is passed through the Polaroid, the light becomes a plane polarized. To detect the polarized light, a beam of light which is passed through the Polaroid and the Polaroid is rotated with an incident beam as axis. If there is no variation in the intensity, the beam of light is unpolarized. If the intensity varies between maximum and minimum along the two mutually perpendicular direction, then the beam of light is partially polarized. If the intensity is maximum in one direction and zero in perpendicular direction, the beam of light is plane polarized. To get the plane polarized light, of course, whatever we have studied, how the perpendicular and parallel direction using, that is main theme of the polarized. And the second one is used in sunglasses to reduce glare. Glare means the shiny material. So Polaroids are widely used in goggles or the sunglasses to reduce the glare. So the light passing through the Polaroid, which is reduced the intensity about the 50%. Similarly, Polaroids are used in vehicles window to reduce the glare or intensity of front vehicle. Similarly, Polaroids which are used to reduce the glare due to the headlights of an automobiles approaching from opposite direction. So this is brought about by fitting the headlight lamp with a Polaroid to give the plane polarized light with a vertical vibration. Then windshield is provided with a Polaroid in a crossed position. As a result, the light which is coming directly from the headlight is completely stopped. The light scattered from the road surface can pass through the windshield since they are unpolarized light. And similarly, the Polaroids are also used as windows in buses, trains and aeroplanes. It helps to reduce or varying the intensity of light inside. Similarly, the Polaroids which are used to produce the 3D waves. So already we know 3D films or 3D pictures. With the help of this, the Polaroids we can use. The Polaroids are also used to improve the contrast in the paintings. So that is a color paintings, the color contrast in old oil paintings. To improve the contrast of the painting, we are using the Polaroids. So this is the end of the chapter wave optics. Just go through it. Thank you.